Just read those slides if you're interested in seeing 3D pictures. But that shows the difference is that this is a model, and this instead shows how it really happens. The blood, that's kind of interesting actually. The blood vessels flow into the gill arches, and then the gill arches are holding the thin layers of the gill filaments themselves, and that's how it really works. It's quite remarkable actually. Very good. It evolved 400 million years ago. Oh, aerial respiration. I don't know the percentage, but the vast majority of fishes breathe oxygen out of the water. However, there are some species that still can get water out of air. Not exactly. We call it out of air, but for those of you who were at the tide pools, for example, I don't know if you remember, but sculpins, when they run out of oxygen, they sort of start gurgling the water in their mouth. A lot of fish have actually water in their mouth and oxygenate it with air, and then they oxygenate their gills that way. So it is still water respiration, but the animals are in air. The most successful ones colonize land, they're tetrapods, but in fact, you have a number of amphibious fishes. This is Periophthalmus, it's called mud skipper. They percolate water, they do all sorts of crazy things. There is actually a really good book. I don't know if we still have books in the library, but in the library it's called Air-Breathing Fishes. This is actually very, very interesting. These animals keep air in their mouth, keep water in their mouths. They oxygenate their gills by gurgling water inside their mouth and then re-oxygenate with their gills. But they also get a little bit of oxygen through their skin. In the case of anabantids and labyrinthids, which are Siamese fighting fish or gouramis, they have actually a structure in their head, in their skull, that is called the labyrinth, where they can gut air from the surface, and the air goes through a very complicated passage in their skull that is very vascularized, and they get they get oxygen out of the air into their bloodstream. The reason for it is because these animals, they live in very confined spaces. In pet stores, you see tiny bowls with Siamese fighting fish. I hope that you've all seen that. And it seems cruel, but not completely, because in many places, Siamese fighting fish live in the puddles that are made out of the hoof marks of water buffaloes, for example. So when the water buffaloes are walking around, they make those depressions. There's a water that is about the size of a fishbowl, and then the fish crawl on land and go in those things, and they live in those things. So, so there is hardly any oxygen, so they need to breathe at the surface. Whoever has started doing their fish skulls, I know that you're hating me, but not nearly as much as a person that I've seen that did disarticulated fish skulls of larval Siamese fighting fish to know when the labyrinth was being developed in the course of the larval stage. So she did skulls of larvae of different ages every day and was able to determine when the labyrinth was being created. I mean, that was really crazy. You say, wow, this is incredible. They have labyrinths, very good. We've talked about purarupus that breathe air, and then they're good to eat, so people carry them around. And then you have lungfishes. There are 3 species, South American lungfishes that actually do breathe air together with the African. The Neoceratodus, the Australian lungfish, hardly ever uses it. When fish are breathing oxygen out of water, what happens is that you have water that goes here, and here there is essentially a barrier that is, the oxygen needs to go through this barrier of, that are the gills. That is this sort of tennis court size area that is going to exchange oxygen between the air, between the water and the blood. Now, in our case, the system is a little bit different than for fishes. The reason why it's different, if I want to summarize it in a very, very schematic way. So we have a heart, and we have lungs, and we have organs. So that's us. And the way it works is that we have blood that goes from the organs into the heart, then it pumps it into the lungs, it gets oxygenated, so there is oxygen here, and then it's pushed back. Because this also goes, our lungs are a little bit like gills in the sense that they are very vascularized and it's a very, very thin tissue, it slows down the blood. And so it slows down it so much that it actually needs to be pumped back out with some strength to give us some blood pressure that is given by the heart, and then it goes back into the organs. Fish, it's not at all like this. Fish is a system, they don't have a four-chambered heart, unfortunately for them. And so the way it works is really complicated. I mean, not very complicated actually. So there's the mouth is here, then there's this. The heart is right behind the gills. So these are the gills. This is the heart. And the organs are here. This is a schematic fish. And the blood goes into the gills. Let me think about this. That's not the way it goes. The blood goes from the organs into the heart. The heart needs to push the blood through the gills, and then it goes straight to the organs. The blood does not come back into the heart. And so the heart has a very, very difficult task in fishes because it needs to take a lot of blood and push it as hard as it can through a wall, essentially. And it pushes the blood as hard as it can because it needs to go through a wall and then have enough pressure to go through the organs, give enough power for the animal to move around, and then it goes back in. So the heart of fishes is under extreme stress. It's a very, very difficult task. There are two types of hearts, and you need to know both of them. There is the heart of a shark and the heart of a bony fish, and the two are quite similar. The concept is the same, but the ones of bony fishes are a little bit more evolved and they do some really cool things. Incredibly enough, I'm not good at drawing, in case you haven't noticed. And there is no good drawing that I can find that shows what I want to show. So I'm going to try to explain how it works, and then maybe I'll go with this one, but it's not good. Okay. Sure, we can use this. I pretend to see this slide for the first time. I've seen it many, many times. Every time I see this, I say, wow, this really sucks. It's terrible. Anyway, I'm going to give it a try. That's fine. You don't really need to remember kind of these things. It may sound nice to know them. That's great. The blood is coming from from the organs, it goes into these things. There's an atrium, there's a ventricle. This is somewhat similar to what we have in our body as well. The ventricle of a shark heart is extremely strong, and this red thickness here is the thickness of the muscle. The muscle is extremely powerful, so it can push a lot of blood. So this stuff is gathering blood, is full here, it pushes it. Here there is a first organ that is called the conus arteriosus. This is the problem that the heart has. So let's say you have the ventricle, it is like this, and then you have this other pouch that is the conus. Now, if the heart was just pushing blood and then filling it back up, the problem is that the animal would get a lot of blood and then would have to wait for the ventricle to fill back up to then get a second jolt of blood. And then wait again. That is not sustainable. The animal needs a constant flow of blood. And so that would not work. And so the way that the animal has solved that is that the conus is actually the most elastic organ of any organ in the animal world. The conus arteriosus of a shark heart is the most elastic organ of all organs. And so this stuff fills up, it pushes it down, and the conus bulges out like this. And when this stuff is filling back up, this one is so elastic that it's going to slowly deflate, providing blood downstream. And before it's fully deflated, this one will have inflated and fills it back up. It's like bagpipes. Does anyone here play bagpipes? I just want to tell you one thing. If you don't know what kind of gas is in the gas bladder and you don't play bagpipes, this is really bad. This is really bad. This class is terrible. In any case, I don't play bagpipes either. But I've seen people play bagpipes. Has anyone ever gone to Rosie McCain's? Yeah, at least we have that. Sometimes you have this short guy that plays bagpipes here. Have you guys seen this guy? This guy is crazy. But look at him. First of all, his cheek gets as big almost as a conus arteriosus, but not nearly as big, because conus arteriosus is the most elastic organ in the animal world, not the cheek of that guy. Instead, he does this, where this is the bagpipe, and this is what is down below. So he's filling it up, and with his arm, he's always keeping the same pressure. This is the same idea. So the conus arteriosus is what keeps the blood pressure constant. It's kind of an amazing design. The fault in the design is here. You have those valves here. There's many of them. And all this effort would be really great if the blood was not flowing back. However, the blood does flow back a little bit because the valves of a conus arteriosus do not close completely. If any of you, 80% of you do, have a heart murmur, 80% of humans have heart murmurs. Heart murmur is when the valves don't close completely. And so when your valves in your heart do not close completely, the blood backflows. And this is the same thing, that you have a major heart murmur and the blood backflows into the ventricle. Not so much that the shark passes out, but nevertheless it's not perfect. So, you know, they have a great conus, it doesn't prevent full backflow. Any questions about this? Because the next one is way more complicated. Not really, a little bit. Teleost fish, it's almost the same thing. The way they evolved is, not exactly, but let's assume that they evolved their heart from a shark heart. So this entire organ, the conus arteriosus, is actually not labeled in this picture, so I labeled it myself. This single valve here is actually the conus arteriosus that has been shrunk into its most simple elements, that is a valve that closes completely. So the entire principle of the bony fish heart is the same as a shark heart, with the difference that there is no backflow. The conus arteriosus has been shrunk into a perfect valve. And so because of that, the function of the conus in the sharks is now taken up by a new organ that's just evolved. It's called the bulbous arteriosus. Does the same thing. You still need to maintain the blood pressure, but because the blood cannot backflow, it does not need to be nearly as extreme as the previous one, and so it is smaller. It is a smaller organ, it's not nearly as elastic, it doesn't need to because it's a lot more efficient. Conus arteriosus replaces the non-muscular bulbous arteriosus, elastic reservoir that dampens pressure oscillations, provides continuous blood supply. So in a sense, once you understand how the heart of a shark works, then the heart of a tilia of a bony fish is really simple to explain. I forgot to mention one thing that I drew it, but I didn't say it, that I think is important. I'm going to try to redo the drawing that I did earlier. You have the mouth, you have the gills, and you have the heart. That's essentially the ends, and then the fish is like this, right? Because of this situation, the heart is it's almost attached to the gills. And in fact, when you get your fish head, when you need to boil it, probably fishermen will either break the head off or will cut it. When you cut the fish head, or if you break it, if you look not in the body, but in the head part, you will see a red dot in the back of the head. That's the heart. The heart is so close to the head that when you break them off, the heart always goes to the head part of the fish. So if you want to know what the fish heart looks like, look on the head part of it, if a person cuts the head. Okay. We need to talk about two more things. Thermal regulation and buoyancy. Thermal regulation. Because there is so little oxygen in the water, salt water or marine, fish need a very large surface area to exchange oxygen between the water and the blood. Because there is such a large area, and there is so much contact between the water and the blood, it's almost impossible for fish to maintain heat. And so because of that, their body temperature is the same as the temperature of the water. It's very much like when we go in the water, we feel very cold because we lose so much heat with water. Imagine the same, but imagine that you would have to spread your body the size of a tennis court. And so it would be really difficult to keep it warm. However, there are a few situations where some fish can be slightly warmer than their environment. These are called endothermic fishes, and by definition, by necessity rather, they need to be large. Small fish are going to lose too much heat. There is no way you can have an endothermic species that is a small fish. So they need to be large animals, and they need to produce heat in the first place, so they tend to swim a lot. Tuna, marlin, sharks, opals, they have a modified circulatory system that has a countercurrent exchange to retain heat. The drawing of the countercurrent exchange system is the very same that I showed you for oxygen, but instead of talking about oxygen, we're going to talk about temperature. The animal is producing heat because it's sweating a lot, very much like when we run, we are hot. So you're producing a lot of, breaking down ATP, so you're producing heat. And the heat is usually lost in the water because what I was explaining earlier, there is a lot of exchange with the water. However, they have a system where the blood that is going to go to the gills goes first through a counter-exchange system where the blood is going to be warmed up by the muscles before it goes into the gills. And I take it back. It's going to be warmed up right after it comes into the gills, and it's going to be cooled off as it gets out. And so, as little heat as they are producing, they are retaining it as much as possible. And so this makes it into a situation where they can retain a little bit of heat, not that much, but some. So some studies have been done where at the beginning people said, well, there's no way they can really do it. But this is a situation where the bottom line there, this is the time, the horizontal line is time. An animal was shot with a temperature probe. It was a marlin or a swordfish, I can't remember now. And, it's a swordfish. And the probe measures both the temperature inside the body, the probe that is inside the body, and then it has a filament that is outside, and it measures the temperature outside. So the temperature outside is the bottom line, and the temperature inside the body is at the top. And then it was sending signals all the time, and so you can follow the temperature, and at some point the animal is actually eaten by a shark, and that's when both of those lines went down and the whole system collapsed. But Barbara Bloch, who works across the bay at Hopkins Marine Station, has those systems that are truly remarkable, where she has probes that she attaches on tuna and does these kind of things, and they go out at sea for several weeks. And then there's a little filament that goes outside of the body, it's attached to a probe that records everything, and then the little filament rusts down, and then it breaks down, and then the probe goes to the surface and opens up solar panels, charges the battery, and then emails the data back to wherever she's receiving the data. So it works really well. The different fish warm up different parts of their bodies depending on which species they are. Some species warm up their brain only. They have those heating organs around the brain. The brain is very tiny over the large eyes. This is the size of the brain. So these are two heating pads around the brain and next to the eyes, because these are fishes that swim very deep to eat squid, and they need their brain and their eyes to be very warm. Other species such as tuna have warm muscles, and they need to migrate into cold water, but they need to maintain their muscles warm to be able to migrate properly in cold water. And depending actually on the species, where the heating organs are is different. If you've seen either a tuna or a swordfish steak, you may see that some parts of the steak are light colored and others are dark colored. The dark colored parts are the heating organs. They just taste just as good as the red muscles that are producing the high temperature. And there's one species that very recently was shown as being fully whole body endothermic, and it's the OPA, this species here. This is really super cool looking. It's an ampliform lamprey, I think it's a genus. Very good. Fine, very good. Now we're going to talk about osmoregulation. Last but not least. Sorry, we are jumping topics, and we have a lot to cover today. Okay, osmoregulation. First of all, osmoregulation is necessary because the water that fish swim in has a certain level of salt, either they're little in fresh water or a lot in salt water, and the solutes, salts and other compounds that are inside the body of the fish are in general different than the outside. And so water tends to go from where there is little solutes to where there is a lot of it. That's the principle of osmotic pressure. And fish need to counterbalance that. There is one species, one group of fishes that do not osmoregulate. Does anyone here remember who they are? I hear fish, I didn't hear hag, but I assume that that's what you were saying before that, so that's great. You still remember that. Brownie points for you guys. So then you need to consider three situations. Freshwater bony fishes, saltwater bony fishes, and sharks. And you will need to know all three things. So let's try to pay attention for the last few minutes, and we're going to get through that. Freshwater fishes. So first of all, the outside, that is the water they're in, has almost no salt. And so it's what it says at the top. These are terrible pictures, I'm really sorry about that. At the top it says, medium is 5 milliosmoles, less than 5 milliosmoles. Essentially it means it's fresh water. There is no salts. Now, when there is no salts, and the fish is kind of salty, the fish itself is 300 milliosmoles. So that's a lot more salty than the outside. Water wants to rush in. And so they have scales that protect them a little bit from that. A little bit of water, fresh water, goes into the body through the skin, not much. But the problem is that because there is so little oxygen in the water and they need to breathe, they need to have a lot of water through their gills, which is this tennis court tissue that is a real curse. They need to breathe, they need to get oxygen, but this means that there is a lot of blood in contact with a lot of water, and the water wants to rush in, and sure enough it does, and so the water rushes in through osmotic pressure into the gills. This is really bad. There is a term, there is a saying that is drink like a fish. Surely not like a freshwater fish. The last thing freshwater fishes want to do is to drink. Because if they were on top of that drinking, that would be an absolute nightmare. They already have way too much water in their body that is coming in through the gills. So they do not drink at all. So you can drink like a fish, and it's fine. It means that actually you're not drinking at all. It absorbs water through the gills and skin. Okay, fine. Now, fish have nitrogen waste. We have urea. Most fishes use as nitrogen waste ammonium. Ammonium is extremely toxic. So actually that's the nice thing about being a freshwater fish. You're going to pee a lot, so they pee out a lot, and they're going to pee out a lot of the water that they're going to get through their gills, and they're going also to pee out a lot of ammonium. So that's actually kind of good. They have a lot of nitrogen waste. It's really bad. You don't want to store it. The kidneys are going to take care of it. So the kidneys are getting out the ammonia and the water. Very long kidneys and stuff like that. So that's good. The problem is that it's very difficult for the kidneys not to expel some salts with this. And salts are extremely precious for those fishes. And so they have specialized cells in the gills. They are called chloride cells. Chloride cells. These are specialized cells in the gills that are going to grab whatever salts are present in the fresh water, which is not very many, and bring them into the body because the fish was not able to retain them. It peed so much that it lost a bunch of salt. So the chloride cells are bringing it in. Chloride cells are specialized cells that have a lot of mitochondria. If you're into cellular biology, it's actually the amazing cells. They have a lot of mitochondria, they use a lot of energy, and they have sodium potassium pumps that bring in salts from the outside into the fish. That's essentially the conundrum of freshwater fishes. Now we're going to go into marine species. Are there any questions about how it works for freshwater species? Marine species. If you remember correctly, the salt content, the solute content, the osmolarity of the body of a freshwater fish was 300 milliosmoles. This guy instead has 400 milliosmoles. So a saltwater fish is slightly more salty than a freshwater fish as far as inside of the body is concerned. So the gradient of salt, of osmolarity between the inside and the outside of the body is not nearly as steep as for a freshwater species. However, because they are marine species, the outside is at 1,000. Now the problem is that this fish, the water wants to get out of the fish. The water is trying to leave the fish, and it leaves the fish from a little bit the skin, mostly the gills. The fish is still breathing, it needs a lot of oxygen, and so it loses a lot of water. The only way to regain water is to drink. And so marine species of fish drink constantly. They're drinking and drinking. So it is true, you can be drinking like a saltwater fish. The problem with that is that you're drinking water, but also drinking a lot of salts, and you want to get rid of the salts. Now, if you were to pee a lot to get rid of the salts, you would lose the little water that you have. That's not very good. You're also producing ammonia. You need to get rid of it, so you need to pee to get rid of the ammonia, and so you need to drink more. The more you drink, the more salts you get in. The saltwater fishes are in a very, very bad place as far as osmoregulation is concerned. So they also have the very same chloride cells, but they work them in reverse compared to the freshwater fishes. They are constantly pumping out the salts all the time. They're in overtime. They're constantly pumping out salts. And they need to pump out salts more than what they drink because they need to be able to pee to get out the ammonia. And so it's really a very, very difficult situation for those fishes. And they manage, but it's really difficult. That's how it works. Does it make sense, kind of? Okay, last but not least. Sharks. Okay. Before I go into the sharks, just 1 second. There are some fishes, diadromous species, catadromous, anadromous species, that move from freshwater to seawater. Salmon, eels, this kind of stuff. Those guys, it's very simple. They go from one mode to the other, and their chloride cells, which are the very same cells, pump salts in one direction in one case, in the other direction in the other. You understand what all the variables are, and you can imagine how you could go from one to the other. Some sharks and some rays live in freshwater. I'll talk about them in a second. Let's talk about the vast majority of them. They are marine species. Unlike bony fishes, sharks use urea as a nitrogen waste, and urea is 2 molecules of nitrogen, as 2 atoms of nitrogen instead of one is 2 molecules of ammonium put together, that you get a urea. And urea is not nearly as toxic. Because it's not nearly as toxic, they actually can store a lot of it in their body. And so first of all, they don't need to expel it. And more importantly, they actually can increase the salt content of their bodies. This is why when you cook a shark, you break down the urea molecule into two molecules of ammonia, and it stinks. It's really gross. This is why I think that they mentioned that people do a lot of shark teriyaki, shark jerky, because most shark flesh is really not very good to eat because it stinks like ammonia. So they have a lot of urea in their body, and because of that, even if, as you can see up there, the outside medium, which is the marine environment, is 1,000, the inside of a body of a shark in the ocean is 1,100. It's not 400 like the bony fish that was in the ocean. It's 1,100. So actually, a shark in the ocean has an osmoregulation problem that is similar to a freshwater bony fish. It's really kind of ironic, but water, salt water, just the water itself, H2O, wants to get into the shark, not out, because the shark is saltier than the ocean. And so everything else that I said about the bony fish that was in fresh water applies to the shark. The difference is that the gradient is not nearly as much. The bony fish was 300 to 0. This one is 1,100 to 1,000. So the gradient of osmoregulation is not nearly as steep for a marine shark as for a freshwater fish, but it's still pretty bad. And so you have water that goes into the gills. The shark is peeing a lot, so it can get rid of its nitrogen waste. So there's a number of things like this. Sometimes sharks go into fresh water occasionally, and some people think that there's a number of reasons why they do that, but one of the reasons for doing that is they want to cleanse their body from all the urea. So they go out there, they remove all their urea to be a lot less salty, of course, and then once they went through their liver cleanse, the kind of cleanse, they go back out and then they live a happier life. I think that's about it. Yeah, are there any other questions about any of, I know that this was a whole lot of things to cover, but the good news, you have a question?
So with sharks, the area is like
To osmoregulate? No, so to osmoregulate sharks, I'm sorry, they retain urea, and so that makes them very salty, but then they have everything else that freshwater fish has. So they have chloride cells, they have exactly what they described for freshwater fishes they have. Not nearly as extreme, but they have all the other things. The only thing about retaining urea is that the gradient of osmoregulation is reversed compared to other marine bony fishes. Very good. I'll see you guys on Wednesday.